Now let's start the crystallography course. We've done the formalities. This will be Chapter 1, Part 2, Sections 1.1 to 1.4. Crystallography is a branch of science devoted to the study of molecular and crystalline structure. We of course include those properties with far-reaching applications in mineralogy, material science of course, chemistry, physics, mathematics, biology. Anybody that wants to know what's really happening inside at a molecular level. The word crystallography comes from the Greek, the ancient Greek crystallis, meaning ice, and graphein, to write. First, this is section 1.2 of the two-dimensional lattices. Before we get to a lattice, let's describe what a crystal is. A crystal is a solid composed of atoms arranged in a periodic array. Of course, these are not atoms, they're cats and mice. In fact, the Anna Marie Van Buren, who made this watercolor, was studying mice with a genetic label of a curly tail, and she included that in this drawing. And by using the abstract cat and mouse wallpaper, so to speak, we can get many of the properties of periodicity. Of course, we're going to apply it to atoms and molecules. This is a model of caffeine monohydrate, and you can see some periodicity there, but it's a little harder to work with, and it's a little intimidating with all those molecules floating around. So for the beginning, we're going to stick to the abstract. So let's consider our periodic design, and the first thing we'll do is we will start with an origin. So here's our origin. We're going to choose arbitrarily the paw of the cat, and now we'll look around for identical neighborhoods, that is other paws, and so we can see we've got lots of other paws along here. And now we have all of the neighborhoods of equal neighborhoods marked out. Now you don't really need the picture anymore, so let's take the picture away, and that is our lattice. Now we started at the paw of the animal. Was there anything particular about the paw? No, we can pick somewhere else, and that is known as a change of origin. So let's change our origin. We can bring it over and put our origin at the nose of the cat, and you can see we have all of the noses of the cats taken, so we have identical neighborhoods. And again, this shows that the lattice of the pattern is not dependent on the origin. Now we can also consider a question. And the question is, how many repeat units, cat and mouse, that is, to the lattice point? Now, whenever you see this question to ponder, what I want you to do is try and answer it before you go on to the answer, which will be given immediately. This would correspond to an iClicker question a little later in the semester. So, how many repeat units to the cat and mouse? That is, cat and mouse is to the lattice point. Well, the answer is 1. There's 1 for each identical neighborhood, for each paw of the cat. We could consider, for example, you can have other choices. You could consider this cat-mouse combination, and then you'd have that cat-mouse combination, that cat-mouse combination. Or you could say consider this group, or there are many others, and we're going to see some of them a little bit later in this presentation. Now let's consider these pictures by Escher, who is the patron saint of crystallographers, so to speak, and let's choose our origin as the eye of the pattern here with the fish and boat. We have a fish and a boat. The fish is sort of straight. Here we have a curved fish and a frog, so they're two different patterns. So let's get the lattice of the above pattern, and there it is. And now let's move it down to the pattern below. And there we have it. We see that, do we have a lattice? Yes. The identical neighborhoods are on the tail of the fish, and so the two patterns have the same lattice. So while the lattice is unique to the pattern, you can have lots of patterns to a given lattice. So here we'll summarize what we just said. The lattice of the pattern is an array of points in space with identical neighborhoods. The lattice is unique to the pattern. One repeating unit for each lattice point. The lattice is independent of the origin. And finally, while the lattice is unique to the pattern is not unique to the lattice. Now let's move on to section 1.3, which is the two-dimensional basis vectors and unit cells. Basis vectors are linearly independent vectors in 3 dimensions A, B, and C, and 2 dimensions A and B that generate the lattice. In the literature we have 3 terms: basis vectors, lattice parameters, and lattice constants. They all refer to the same idea. That's unfortunate, but that's the way it is. And we can often refer to the scalar values rather than the vectors. So we can have A, B, and C, and the angles between them, which we'll describe later, alpha, beta, and gamma. Now we have a two-dimensional lattice. Let's lay out a basis vector. We can choose any origin, and we can connect any 2 lattice points. The only condition is that you can't have any other lattice points between your 2 lattice points that you connect. For example, you can connect these 2. That's a lattice. That can be a basis vector, but you can't connect these 2 because you'll have this intermediate one. That's the only thing that you have to watch out for. Now we can choose that will produce a one-dimensional lattice, so you can do any sort of multiplying and translating, you'll get 1 lattice. Now if you the second basis vector, and it has to be independent of, it can have 1 lattice point in common, but it can't of course have 2 because then it wouldn't be different. And you can again, the only criteria is you can't have an intermediate point. So you could pick this one, and you cannot pick this one and this one, but you can pick this and this. The basis vectors have a handedness. On the right, we have a right-handed system. This is a right hand, and we have, if we put our hand here such we have the A going into B, our thumbs will come up towards us. That is known as a right-handed system. On the other hand, if you have A into B, you have to have your thumb pointed down, and that means a left-handed system. So here we have the same lattice. Here's this lattice just continues on, and we're trying to label it. Another word for labeling is to index. So we have A laid out along to the right and B up, and that gives us a right-handed set. And we could also have done it the other way around. We could have had A up and B down, and so we could have had a left-handed basis systems. So you have one lattice, but the lattice, you can label it or index it as either right or left-handed. So let's have our question to ponder. The question, is the lattice above right or left-handed? Now what do you think? Well, the answer is that it's neither. Handedness is a property of basis vectors, not lattices. Let's describe the lattice mathematically. A primitive unit cell is a unit cell with only one lattice point. Every lattice has a primitive cell. For a primitive cell with basis vectors A and B, we can write them out mathematically as the translation T is a linear combination of vectors A and B, and we can have the coefficients be integers, and those integers can go from minus infinity to plus infinity, both the u and the v. So here we have a lattice The yellow marks the origin. I'm going to lay out an A vector along, basis vector along here, and that's going to be 1, 0. And if I come to this point, it's 2A, so it's 2, 0, 3, 0. And if I come, now if I want to lay out along the B axis, I go to 0, 1. And if I want to come back the other way, I go minus 0, or 0 minus 1. But crystallographers tend to use private notation. They put the line above the 1, and they call it 1 bar. So you have 1, 0, 1 bar. So here we have it. If we come back along A, it's 1 bar, 0. If we come minus B minus A, we come to 1 bar, 1 bar. So it's like any other labeling system that you've used for your coordinates. So here we have 4 over and 1 up gives you 4, 1. Now we have primitive cell here, and the question is that we have one lattice point to the primitive cell, and how can we show that? Well, it's not too convincing here. You have sort of a chip, a little corner, and a little corner, and a little corner, and do they truly add up to a full circle? Especially when these cells are not necessarily orthonormal. Let's change the origin. So if we change the origin, you can see that now it's clear there's a one-to-one relationship between each primitive unit cell and the lattice point. Now let's set out a unit cell. We're arbitrarily taking the eyes, and we're choosing the lattice vectors A and B, and here's our unit cell. And now let's cut that unit cell out and take it over here on the side, and let's see what we can do about it. The unit cell contains all of the information necessary to create the whole pattern. Well, let's see, is that true? Well, here's our fish, but his front of his nose is missing, so here's the nose coming out like that, and we can see that this nose could be picked up at this corner, and there it is. And likewise for the top of his head, could be picked out down below, and there's the top with the little top fin, and here we have the back fin is over here, and if you can do the same with the boat. So all of the information that you need to create the whole lattice is found within the unit cell. What's different is that sometimes it's hard to see what the pattern is. You might not necessarily see a boat and a fish pattern just looking at one unit cell cut in this way. So we need to put them all together sometimes to see the pattern. And you'll see that in crystallography. When you actually get to atoms, that'll be a very important factor. So here we have it. The only information needed to construct the pattern is contained in the unit cell, which is repeated many, many times. For each lattice, there's an infinite number of choices of primitive cell. So here's this 3 different primitive cells, and they're called primitive cells, of course. So now let's have a question to ponder. The question to ponder is, what can you tell me about the area of each of these primitive cells? You think about that. Well, the areas are all equal. That might surprise you, but if you think about it, each primitive cell has one lattice point. We showed it last time. Each lattice point is associated with the repeating unit. The area of the repeating unit is the same, hence the areas of all the primitive cells are all the same and are equal. Sometimes, however, we need to have a multiple cell. And if you were labeling this would be indexing this cell, for example, it would be 00 and 10 and 00 and 01, and this center point would be halfway over and halfway up. So for a non-primitive cell, the interior points are going to be fractions. The question to ponder is, how many lattice points does cell A have? Well, here's cell A. How many lattice points does it have? Well, I think you got it right. 2. 1 for the corners, which we showed in that animated video, and 1 in the center. Another question, what is the ratio of the area of cell A to cell B? You think about it. I hope you're right. The ratio is 2 to 3. Now we'll move on to section 1.4, which is the two-dimensional transformations between sets of basis vectors. First of all, we'll take A1 and A2, we'll lay that out, and then form the unit cell from A1 and A2, and we'll start out with the same origin and have a new A2 and a new B2. If we want to relate the blues to the reds, the 2 subscripts to the 1 subscript, we can see if we want to go A2, which is from here to here, we could go 1 along A, and we'd have to go negative B to come back to this point. So here we have it, A2 is equal to A1 minus B1. Here's a point to ponder. What is B2? You figure it out. Hope you got it right. B2 can be written as, here's B2. It could be written as 2 times A, 1, 2 times A, and then 1 up for B. And now if we want to write the transformation, we write the row vector A2B2 is equal to A1B1 times the transformation matrix P, and we can see all we have to do is have these two equations satisfied. So if we look at what's A2, we can multiply A2 is 1 times A1 and minus 1 times B1, and you can see you take the coefficients of the A equation and you lay them out in a column. The same with the B, you take the coefficients of the B and you lay that, the 2, 1, and you lay that out on the second column. So that's how you get your transformation matrix P. Now let's see if we can see some interesting facts about the transformation matrix. We could take the determinant of the matrix, and we see that the determinant is 3. That is, it's 1 times 1, which is 1, minus 2 times minus 1, which gives me 3 altogether. So this is going to show me 3 related facts. 1, we see that the determinant of P, which is 3, is greater than 0. Therefore, the transformation keeps the handedness. In this case, we have a right-handed system going to a right-handed system, and we have a positive system. If we started out with a left-handed system, then we would, and the determinant of the transformation matrix was positive, you would go to a left-handed system. On the other hand, if you have a negative term, that is, that the determinant of P is less than 0, then you change handednesses. The left goes to the right, or the right goes to the left. Now what happens if you're smack in the middle, you have the determinant equals to 0, then you do not have linearly independent vectors, so it's not a valid set of basis vectors. So if you're asked, prove that this transformation is not linearly independent or is linearly independent, you take the determinant, and if it's equal to 0, it's not linearly independent, and if it's not equal to 0, then you are sure that it's linearly independent. And finally, if you take the determinant of P, you can see that that's going to be, in this case it's 3, and we can compare the number of lattice points in the new unit cell with the old, and you get 3 to 1 here. And Now I'm going to do some homework for you. It's a special present for you. The first homework, and I want you to follow this format, is in your Scholar or on the web. You'll see that you can copy this figure and you can copy the assignment. So I expect you to copy both the assignment and any associated figure if there is one, and then you can make the figures larger or manipulate it in such a way as to make it easier to work with. And now you're asked to draw the lattice. So you want to draw the lattice points. So I took my point here as my common, and I'm going to look for all other points that have this neighborhood of the two dots slanted in this direction, the two red dots. And if you come over here, here's another one that's like that. And so I have marked that on this diagram below. We could choose any point in this pattern, and then we just look for the identical ones. If you're on the molecule, it's a little harder to see, but go look and you'll see that it works just fine. And now you want to have a primitive lattice, so we need to connect these lattice points. So here are the lattice points that we're connecting, and it forms the primitive cell. There are other ones that you could have taken. I could have taken other points here. For instance, I could have taken this, 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 and this. However, that would not be a primitive cell since it contains this central point. I could have taken this, 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 and this, and that would give me another primitive cell. So you have to answer the question, is this cell unique? Well, it's not, because there are many cells that I could have chosen. I've just demonstrated a few. So that's it for this part. So long, guys. See you next section.